All right, so you got oh great, your pen. Sorry. So you this is an AP Warren question, right? So we did this lab where you graphed weight versus mass. What did it look like? So this was a line. So you collect the data. I think it was the assignment where you had pictures of a spring scale and masses hanging. Remember that? And you got this line. Do you remember what the slope was? Okay, it was really close to 9.8. And what are the units? What are the units? Over. So this was your slope. And your intercept was very close to 0, which makes sense because if mass is 0 kilograms, then the weight should be what? If you have no mass, so weight should be 0 too, right? So all you got to worry about really here is the slope. And what does the slope mean? For every good. For every kilogram of mass, what's happening as you go 1 kilogram this way? How much do you go up? 9.8. Good. And what is that that's increasing by 9.8? What? Good. All right. So the weight, every time you go 1 kilogram more in mass, the weight increases by 9.8 newtons. Yeah? So you got a change in force due to gravity that happens for every kilogram you move to the right. Now, where do you think this equation is going to be valid? If I write like an equation of this line, what do I get? Weight equals what? And another word for weight is force due to gravity, right? And what's that going to equal?
9.8 times mass.
Good. 9.8 what? What are the units? 9.8
newtons
per
mass per kilogram.
There you go. Per kilogram times mass, right? We call this thing that you described, the slope, we call that G. And we write M for mass. And we could write FG there, right? On your equation sheet, you'll find that equation. And the way they write it is FG, they have a vector symbol because that's towards the center of our planet, equals, and they write it the other way, MG, I think. And this works only on Earth's surface. Only on Earth's surface, G has a magnitude of 9.8. And that's newtons per kilogram. Now, do you recognize 9.8 from earlier in the year? It was also what? What? What do you mean gravity? Well, that's what this is. 9.8 newtons of force is how much the Earth pulls for every kilogram. But when we drop something through the air and graph velocity, this slope, let's say down is positive, we would get a graph like that with a slope of 9.8 meters per second. And that also has the symbol G if you're on the Earth's surface, 9.8 meters per second. And interestingly enough, I'm going to do this over here, 9.8 newtons per kilogram is the exact same thing as a meter per second squared. Because a newton, whoops, I don't want to do that. A newton, if we look at second law, which we just did now, we get this, right? That's second law. What are the units for force? How do you measure? Newtons. What are the units for mass? Kilograms. What are the units for acceleration?
Mass over
Meters.
meters over seconds squared.
Good. So our definition of a Newton comes out of Newton's second law. This is Newton's second law. This is our definition of a Newton. Okay? A Newton is a kilogram of mass with a meter per second squared of acceleration. That would be 1 Newton of net force to cause that. Okay? And so if I plug that in here for newtons, you'll notice that I get 9.8 kilograms meter per second squared over kilograms. Again, all I did there is I plugged in for newtons based on our definition. What do you see I get as my units? When the kilograms cancels, I get what? 9.8,
Meters per second squared.
which is exactly the same thing as 9.8 newtons per kilogram. Nobody knows why, but if you're on the Earth's surface, you get the same exact number as your acceleration due to gravity in meters per second squared as your gravity field strength, how much the Earth pulls for every kilogram. So the strength of our gravity field is identical to our acceleration due to gravity. And if you go at different places in the universe, nothing changes about this graph except the slope. If you go on the moon, just like the problem here, the slope just becomes 1.62 meters per second squared.
So do I substitute
That-
for G?
That's your acceleration due to gravity at that place in the universe, but it's also your gravity field strength at that place in the universe. So if you know the acceleration where you are, the free fall acceleration, you know the strength of your gravity field. You can find out your weight. If you know the strength of your gravity field, you can figure out your acceleration when you're in free fall. And again, nobody knows why. That's why we're taking matter and blowing it apart and looking what's inside. Sorry for babbling so much.
No, it's fine.
You were kind of had it figured out in the first second I talked too much.
It's fine.
Later. Cool.